Hello and welcome to the last new series test. We're going to talk about the alternating series test. So, definition, what is an alternating series? A series whose terms alternate between positive and negative is an alternating series. The nth term is always of the form an equals negative 1 to the n plus 1 times bn, or an equals negative 1 to the n times bn, where the sequence bn is the absolute value of an is always positive. In other words, an alternating series will always have a negative 1 to some exponent, and we can always reduce that exponent to either n or n plus 1. Note that in the last section, we looked at series that did not have all positive terms, but alternating series are not the only series that have negative terms. For example, consider an equals sine of n pi over 6. This sequence, this alternates, no it doesn't, that's what I'm trying to say, it does not alternate. This oscillates between positive and negative but is not positive, then negative, then positive, then negative. If we were to write this out, a1 would be sine of pi over 6, which is positive. a2 would be sine of pi over 3, which is positive. a3 would be sine of pi over 2, which is positive. I'm just going to dot, dot, dot. So we get to a6, which is sine of pi, which equals 0. And then, and then a7 is sine of 7 pi over 6, which is negative. So really, it has 5 positive values, a 0, and it's going to have 5 negative values, and then 0, and it's going to repeat that pattern. So not all series that have negative values are alternating. So we saw if the series has negative terms, we can use the ratio in the root test, and that's true for the alternating series. But in this special case, we can actually use a different test. So the alternating series test says that the series summation from n equals 1 to infinity of negative 1 to the n plus 1 times bn, which we will say is equal to, let's write this out, that's b1 minus b2 plus b3 minus b4 plus dot, dot, dot. So it's alternating between positive, negative, positive, negative. And note we have here that bn is always positive. Then this series converges if both 1, bn is bigger than or equal to bn plus 1 for all little n bigger than or equal to some capital N, all this is saying is that the Bn are decreasing for some point on. And 2, we need that the limit as n goes to infinity of Bn goes to 0. If it doesn't, then the alternating series, the nth term test for divergence just immediately says it diverges. So let's see an example of this in action. Consider the alternating harmonic series. Alternating. This is a well-known series, so we'll underline it just because it has a name. So the harmonic series was the sum of 1 over n. The alternating harmonic series is the sum of -1 to the n plus 1 over n. So the alternating harmonic series converges, unlike the harmonic series, which diverges, since 1 over n decreases. Why is this? You should always verify why this is. If we let f of x equal 1 over x, then f prime of x is -1 over x squared, which is negative for all x, so it's decreasing. And 2, the limit as n goes to infinity of Bn, which in this case Bn is, as I set up here, but I didn't ever explicitly state, that is strip away the -1 to the power. So the limit of 1 over n is just 0. So the alternating series test says that this converges. So let's do another example. That one was kind of easy. Does the summation of -1 to the n times 10n over n squared plus 16, does this converge? Oh, one last comment. Note, the alternating harmonic series, this converges. However, if you add the absolute value, this does not converge. So that means that this is a conditionally convergent series. Okay, back to the example. So we're going to use the alternating series test because we have that -1 to the n. The alternating series test. So 1, strip away the negative sign. What are we left with? 10n over n squared plus 16. This decreases. Why is this? If we have f of x equals 10x over x squared plus 16, take the derivative using the quotient rule. This is 10 times 16 minus x squared divided by x squared plus 16, quantity squared. And notice 10 is positive. The denominator will always be positive. And the 16 minus x squared will be negative, making it negative if x is greater than 4. So this decreases as long as n is greater than 4. But that's all we need. We need it is decreasing for some point onward. And 2, we have the limit as n goes to infinity of 10n over n squared plus 16. This equals 0. So the series converges. That's the alternating series test, done. But let's add some more information to this section, because that's kind of a short section. So the alternating series test and alternating series in general are very nice because we get nice error estimates. So we haven't talked about error estimates yet in terms of series. So let's do that now. The error estimates for alternating series says if the summation of -1 to the n plus 1 bn, if this satisfies the alternating series test, so it was shown to converge using the alternating series test, then for little n bigger than or equal to that capital N, if the nth partial sum, Sn, satisfies, I'm defining this notation again, if Sn is the nth partial sum, then the absolute value of L minus Sn is less than B sub n plus 1. Where L is the actual sum. So what is this saying? That is, the nth partial sum approximates the actual sum, the actual series, with error less than the first unused term. So finding the error for alternating series test, super easy. You just take, okay, we're doing the 12th partial sum, so the 13th term is my error term. Furthermore, we can say a little bit more than this. We have the summation of -1 to the n plus 1 bn, so the actual series will always lie between any two successive partial sums. And label those sums Sn and Sn plus 1. So let's see this in action. Let's see what we mean by all of this. Example. Consider the summation from n equals 0 to infinity of -1 to the n times 1 over 2 to the n. This is an alternating series because we have this -1 to the n. But notice we can also combine this, and we have the summation from n equals 0 to infinity of -1/2 to the n. This is a geometric series with absolute value of r, which would be 1/2, is less than 1. So we know that this converges, and we know it converges to 1 over 1 minus r, which is -1/2. Simplify this, and we know that this series converges to 2/3. But we know what the series is, but now let's talk about this error term. So we can truncate this sum at the 8th term. I think I missed a letter in 8th. I think there's supposed to be an H in there. There you go. So what would that look like? We would have the summation from n equals 0 to infinity of -1/2 to the n. Truncated at the nth term, so we would have 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus 1/32 plus 1/64 minus 1 over 128. That is our 8th term. So we're going to stop it right there. But the next term is 1 over 256. So the error in approximating 2/3 as this S8, which is exactly all of this, is less than the next unused term, which is 1 over 256. Moreover, we can also say that S, which is our actual sum, which is 2/3, is bounded between any two consecutive partial sums. So it is less than S9, but greater than S8. And we have S8 written up here. S9 will just be adding this 1 over 256. And using a calculator to figure out what this is, we know that 0.664 is less than or equal to 2/3 is less than or equal to 0.668. Now we know what 2/3 is, so why do we care about this? This is just a nice way to see this without getting too complicated. One more example. It doesn't use the error estimates, but I decided to throw this in because this is a very common series that we need to be able to talk about. So since 1 over n to the p decreases to 0, for p greater than 0, we have that the sum from n equals 1 to infinity of -1 to the n plus 1 over n to the p. So this is our alternating p series. First off, we have that this converges absolutely for p greater than 1. We know that if you strip away the negative sign, then we have the normal p series, and that converges. And 2, unlike the normal p series, this also converges, in this case conditionally, for p between 0 and 1. So it seems like, based off of the alternating series test and the alternating harmonic series, it seems like adding this -1 to the n plus 1, making it an alternating series, can make things converge that don't normally converge, which is kind of cool. And last thing for this section is just a little fun fact. Not going to test you on this, just really interesting to think about how delicate some of these series are. So this is the rearrangement theorem for absolutely convergent series. So this theorem says that if the summation of an converges absolutely, then you can reorder the sequence an. And the corresponding series converges absolutely also. And moreover, it converges to the same thing that the summation of an converges absolutely to. So why is this a fun fact? Cool, we can rearrange the order. You kind of expect that. I mean, who cares in what order you add things? But remember that this deals with infinite things. So we don't really know how infinite things behaves too well compared to finite things. And what makes this a fun fact is this is not true for a conditionally convergent series. So I'm going to show you an example of this. Consider the alternating harmonic series. And we know that this converges, but we know that the harmonic series does not converge, so this is a conditionally convergent series. So since this is an alternating series, we know that what this sums up to, so L, this has to lie between S2, which is 1/2, and S3, which is 5/6. In particular, if it lies between those two, those are both positive, then we know that L does not equal 0. Now, suppose that we reorder the sequence -1 to the n plus 1 over n. So we're going to do that by looking at 2 times L. 2 times L is 2 times, we have 1. The next term would be subtracting off 1/2. Then we're adding on 1/3, subtracting 1/4, adding 1/5, etc. Just going to keep writing them because I use them all. Well, this is, if you distribute the 2, this is 2 minus 1 plus 2/3 minus 1/2 plus 2/5 minus 1/3 plus 2/7 minus 1/4 plus 2/9 minus 1/5 plus ... Now we haven't actually rearranged our sequence yet, so let's rearrange it now. We're going to leave the first 2 the same, 2 minus 1. Then let's look at the minus 1/2 next. Then let's look at the 2/3 minus 1/3, coming from 2/3 minus 1/3, so we have rearranged it. And then we have minus 1/4 plus 2/5 minus 1/5 minus 1/6 plus ... We'll go ahead and perform the subtraction in all of the parentheses. 2 minus 1 is 1, minus 1/2. 2/3 minus 1/3 is 1/3, minus 1/4. 2/5 minus 1/5 is 1/5, minus 1/6, plus ... And this is exactly L. This is what we wrote up top in the brackets. So when we rearranged it, we got that it equals L again. So we have 2L equals L. The only way this is true is if L equals 0. But we already showed that L cannot equal 0. So that means that this operation of rearranging the terms was invalid. So we cannot, forgot the we, rearrange the terms of a conditionally convergent sequence. Series. And that finishes this section. The main thing to take away is the alternating series test, and that if you have an alternating series, the error term, when you look at the